I'm wearing a mask because although I've gotten negative test results on COVID, I've been coughing a whole lot recently, so in keeping with my general paranoia, I'm wearing a mask today. Also, so you get to experience the thrill that students had over the past couple of years of having a mouthless person talk to you. I am your father. I assume you have all this committed, so we don't have to talk about it later. Any questions?
How was your week or weekend?
The break, spent a lot of time in coffee and like it is. Other than that, it was fine. We had a guest coming in on Saturday, so a good chunk of time was spent pretending to clean up. And yours?
I slept a lot.
In between studying physics, yeah.
Yes, in my sleep.
Yeah, excellent. All right, other questions? Perhaps related to the class or something? What was the last thing we did?
Work and energy relationships.
So we didn't do any examples, we just sort of left that cliffhanger. So the total work is equal to the change in kinetic energy. You know I'm gonna ask pretty soon, so if you don't know what the formula is, you might want to refresh your memory. Non-conservative work is equal to the change in energy. And work let's make it more generic. All right, if you have no idea what that symbol is, that's okay, because it's out of scope, but for those of you who have had a little bit of calculus, that's the official definition. But if force is constant, work is force times displacement. It is a dot product, meaning we care about the parallel parts. Also being a dot product, the answer is a scalar, so there's no direction for work.
Is that an R on the, like the,
That,
no, the two on the little squiggle?
oh, yeah, those are R's. The integral of f dot dr from R initial to R final. I was in elementary school, and the teacher was talking about, I think we were doing areas of rectangles, length times width. And the teacher talked about how do you find the area of something that's not a rectangle, that, you know, how do you find the area of something that looks like that? She talked about making a whole bunch of little rectangles and finding the area of each tiny little rectangle. And then years later, I realized that my third grade teacher knew some calculus. In essence, this is just breaking up a function into a whole bunch of little rectangles and adding them together. All right, so let's just do a quick example. I have a box, 4 kilograms. I push on it with a 3 Newton force. and the box goes 2 meters in the direction in which I'm pushing, how much work is done?
6 newtons. Oh, 6 joules.
Okay. Or Newton meters. So 3 newtons times 2 meters. 6 Newton meters, or 6 joules.
Is there a preferred answer?
Is there a what?
Preferred answer? Like, would you rather NM over joules?
You're more apt to see joules. So that's what I'm accustomed to. However, they're both equally right. That's not one of the things I get too hung up about. All right. Well, that was simple enough. At least we had one person who knew it. I'll take my 4 kilogram mass here. It's gonna displace 2 meters. This time I'm pushing this way with 3 newtons of force. What is the work done now? The proper wording is, what is the work that 3 Newton force is doing on the 4 kilogram mass? So we want to go for it. The worst that happens is you're wrong.
Well, I don't think it'd be negative because we don't know which way is negative. So would it also just be 6 joules? Would it just also be 6 joules?
It would not also be 6 joules. It's moving to the right.
And there's a force.
Yeah. It's the runaway truck and you're trying to stop the truck.
One joule.
No. How'd you get 1? Is that just a guess?
No, I was thinking like 3 newtons this way, 2 meters, and you get this way. No, 3, 2, subtract it.
Oh, then why didn't you say 5 for this one?
Oh, because on that one I could.
The same rules should pretty much be applying here. Ali,
I want to see 0.
okay, it's not 0.
Negative 6 joules.
It is indeed negative.
Okay. Well, because we're pushing against it as it's slowing down.
If you think about it, if you are pushing in the direction it is moving, it will speed up. The force is in the direction of velocity, therefore acceleration is the direction of velocity, it will speed up. If it speeds up, kinetic energy increases. So the work done is positive because there's a positive change in kinetic energy. Which of course brings up the question, and I'm about to hear that chorus of angels, what's the formula for kinetic energy? All right. We have talked about formula for kinetic energy.
1/2.
All right, well, I'm going to ask again. The chorus of angels. Anybody still need to look it up before I ask? What's the formula for kinetic energy?
1/2.
All right, not quite the group of angels I was hoping for, but good enough for now. Kinetic energy is related to the speed of an object. The greater the speed, the greater the kinetic energy. So if any part of your push is in the direction of movement, you will make it go faster. If any part of your push or of the force is against the direction of movement, you're going to lose kinetic energy because you're going to slow it down. Losing kinetic energy means you're doing negative work. From a dot product point of view, if I have A dot B, which is, again, equal to B dot A, it's the magnitude of A times the magnitude of B times the cosine of the angle between them. So if they are in the same direction, what is the angle between them?
There is now one. There isn't one. This is 0.
Yeah, 0. So cosine of 0, that's supposed to be a 0. What is the cosine of 0?
1.
All right, if they are opposite directions, what is the angle between them?
180.
Degrees.
Thank you. And the cosine of 180 degrees,
1. -1.
that's why you get negative work, from a math point of view, the way it's negative. If you think of this as a cosine axis here, cosine of some angle. Any angle, and this is the angle here, anything within this region right here, actually, within this region, you have a positive x value or positive cosine value. Anything over there, you get a negative cosine value. So anything from 90 degrees to negative 90 degrees, it's positive. At 90 degrees and negative 90 degrees, cosine is 0, because on my axis here, it's 0. There we go, math 172, that's the essence of it right there.
That's what I just started.
And now you know it all. All right. So now I got my 4 kilogram mass that's going this way 2 meters. And I'm pushing this way on it with 3 newtons. What is the work done on the 4 kilogram mass by the 3 Newton force?
I want to say 0 because we're not moving in that direction, but I could be.
Sometimes you just need to seize what you want. Go for it.
I just think it'd be 0 because we're not moving in that direction.
That is absolutely right. The only thing I can give you on is units.
So 0 joules.
But it's a force, no? It's still a force.
Yeah,
Oh, but it's a vector, so it has to matter with which direction.
oh, absolutely. In the case of work, it matters in which direction is it relative to the actual displacement.
So because the force is not acting against or for the direction of motion, it is 0.
That is correct. Looking at it from a more math formula point of view. We have, let's just go for traditional I hat, J hat. My work is force times displacement, which is -3 newtons J hat dot 2 meters I hat. What I care about the dot product is I care about the vectors, so the rest of it I'm just gonna pull out, so I get -6 joules J hat dot I hat. And they are not parallel to each other. Matter of fact, they're perpendicular more specifically. If J hat and if I'm doing a dot product between perpendicular vectors, 0. What's the formula for potential energy? Oh, there's 2 things wrong with that. First off, what do you mean by gravity?
Isn't the force of gravity? Or
Mass times the force of gravity?
yeah, the force of gravity. Or, 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 yeah, the force of gravity.
total, or like energy minus kinetic energy?
Oh, total energy minus the kinetic energy. Yeah, that would be potential energy, not the formula I was going for, but
Or, conserve energy? Or conserve work?
conservative work, that's the negative change in potential energy, it's not the potential energy itself. And Ali, the other acceleration due to gravity, I think is what you're going for, not gravity. Yeah, gravity.
Oh, yeah.
Oh, surely we went over potential energy,
Yeah,
or did I not?
I don't think so.
I just assumed I did it in another class, so you did it here.
You.
Ah, okay. All right, so the correct response, when I asked, what's the formula for potential energy?
Which one?
That's the right question. What did I ask them?
I remember now.
Okay. Why, which one?
Because you have, it's a great question, Dr. Fox.
Well, thank you.
There's
I'm expecting a great answer.
There's two different types. There's the non-conservative and then the conservative work.
That's true, but potential energy is associated with conservative. All right, apparently you were studying the wrong physics as well over the holiday. Or working, something, or sleeping. I think that pretty much sums it up right there.
What is?
For every conservative force, there exists potential energy. So, because there's multiple conservative forces, there are multiple potential energy formulas. If the force, so we'll set up the conservative force. And what are all the conservative forces, by the way?
Gravitational force, elastic force. Say it.
Oh, electric force.
Flash magnet.
And then the elastic, the electric,
Magnetic.
What's that little upside down mountain?
that
Yeah.
for every,
Oh, physicists are really lazy.
this is mathematician. This is the lazy math people.
Oh.
For every conservative force, there exists potential energy.
So this translates to for every.
So, did I need to see some of these notes again. There you go. So we got into the list. Okay. So let's actually derive one of these formulas. We're gonna derive something very similar to what Ali mentioned. I have an object that is moving upwards. I have a planet down here. It's gonna go up, well, let's say it starts out at some initial height, hi, and goes to some final height, hf. I know that the conservative work is equal to the negative change in potential energy. So let's take a look at, so conservative work equals negative change in potential energy. Conservative work is the conservative force, dot displacement, which is negative U final minus U initial. What are all the forces acting on this mass as it goes upwards?
Force of gravity.
Okay. Anything else? Not based upon the little that I gave you. All I said was moving up, I didn't say whether it's being lifted or thrown, but it doesn't matter if I'm lifting it, well, I'm applying a non-conservative force, so it doesn't really apply to our problem here. And if I'm throwing it, well, I'm ignoring air resistance anyway.
And we're only really working, well, what if you, hit it with a bolt of lightning that shot it up?
Once it is in the air going upwards, I'm assuming the lightning was just at the initial, that was the impetus to get it to move, then I don't care about the lightning. All I care about is while it's going up.
Okay.
So, let's just make up positive because why not? My conservative force would be negative W times my displacement, which is H final minus H initial, equals negative U final plus U initial, distributing the minus sign. Formula for weight.
MG.
All right, so I got negative mg H final minus H initial equals negative UF plus UI. So distributing, I get negative mg H final minus, plus mg H initial is equal to negative U final plus U initial. The work energy relationship gives us this. We now have to think of a formula for U that would make this true. What can we let U equal so that this equals this?
We gotta let it equal something.
All right, let's see if we can narrow that something down, because something, again, huge category. The actual answer was smaller. And at the same time, infinite.
MG.
If U equals mg, then this becomes negative mg plus mg